Hello students, let's discuss the physics paper 2023. This is set 155 2 by 1. As you know, there are total 35 questions and it was divided in 5 sections. Section A, question number 1 to 18, MCQs. Section B, 19 to 25. These are also short answer questions, 2 marks each. Section C, 26 to 33 marks each. And in section D, 31 to 33, which were long answers, 5 marks each. And there were 2 case-based study questions, 34 and 35. Let's start from section A, question number 1. First question is, the magnitude of electric field at a distance 4 meter is 9 Newton per Coulomb. Okay, for the same charged object, you have to find out the distance when the electric field is 16 Newton per Coulomb. We know that the electric field due to a point charge is given by E is equal to KQ by R square, where K is constant of proportionality 1 upon 4 pi epsilon naught. Here when electric field is 9 and the distance is 4, so the equation becomes Q upon 4 square, that is 16. Let this is equation number 1. Now here when the electric field is 16, you have to find out the distance. Let the distance is R dash, so it will be R dash square. Let this is equation number 2. So dividing 2 upon 1, we get 16 upon 9 is equal to, left hand side we have divided 16 by 9. Right hand side when we divide, this comes out to be 16 upon R dash square. So 16 and 16 cancels out. R dash will be equal to 3 meter. Hence the correct option is C. Question number 2. A point P lies at a distance x from the midpoint of an electric dipole. You have to find out the electric potential. How is it proportional to the distance? We know that for an electric dipole, the potential on the axial line is given by K. K is constant of proportionality 1 upon 4 pi epsilon naught upon R square minus A square. Kp upon R square minus A square, where P is the dipole moment. Here R is equal to x, so it can be written as Kp x square minus A square. 2a is the dipole length. Okay, so here we can see that the potential is inversely proportional to x square. Hence, the A option is correct. Question number 3. A current of 0.8 amperes flows in a conductor of 40 ohms for 1 minute. You have to find out the heat produced. We know that the heat produced is given by I square R into T. I is given as 0.8 ampere. So it becomes 0.8 into 0.8 into 40 ohm. Then time is given in minute. So 1 minute is equal to 60 seconds. On simplifying it, you get 1536 joules. So the B option is correct. Question number 4 is, you have to find out the internal resistance of the cell. Internal resistance of the cell in terms of EMF and potential difference, terminal potential difference, it is given by E minus V upon V into R. Hence, the D option is correct. Question number 5, beam of electrons and protons are moving parallel to each other in the same direction. Let the electrons are flowing in this direction. So the conventional direction of the current will be taken opposite to the flow of the electrons. So this is the direction of the current due to the flow of electrons, and the protons are also flowing in the same direction as that of electrons. So I2 and I1 are in the opposite direction, and we know that whenever two current carrying wires are parallel to each other and the current is flowing in the opposite direction, they repel each other. Question number 6. A long straight wire of radius A carries a current I. Let us draw the figure. This is a long straight wire whose radius is A and the current flowing through it is I. Okay, the magnetic field B1 at A by 2. A by 2 will be, if this is the center of the wire, this much distance will be A by 2. So the magnetic field here is B1 and the magnetic field at a distance 2A. 2A will be outside the wire somewhere here. So this distance is 2A. Now here you have, first you will find out B2 and B1. First let's find out B2. The magnetic field outside due to a long current carrying wire we know is equal to, B2 is equal to mu naught I upon 2 pi r. Here r is how much? 2A. So mu naught I upon 2 pi into 2A. So it will be 4 pi A. So outside B2 is given by this. Now inside, using Ampere circuital law, B1 into 2 pi r. Here r will be equal to A by 2. Inside r will be equal to A by 2 is equal to mu naught into I dash. First let's find out I dash. For cross-sectional area pi A square, the current is I. For the cross-sectional area pi A by 2 whole square, let the current is I dash. So solving it, we get I dash is equal to I by 4. Okay, and here r is equal to A by 2. So substituting r is A by 2 and I dash equals to I by 4, we can find out B1. So B1 into 2 pi into A by 2 is equal to mu naught into I by 4. 2 and 2 cancels out. So B1 is equal to mu naught I upon 4 pi A. So here we see that B2 is mu naught I upon 4 pi A. B1 is also equal to mu naught I upon 4 pi A. So the ratio of it is equal to 1. Hence the correct option is B. Next is the direction of the propagation of the electromagnetic wave. We know is equal to E cross B. Next is a ray of monochromatic light propagating in air is incident on the surface of water. Which of the following will be same for the reflected and refracted rays? Energy changes, speed changes, wavelength changes. What remains the same for reflected and refracted? The frequency is the same. Okay, whenever the ray of light passes from one transparent to another transparent medium, that is refraction, frequency remains the same. A beam of light travels from air to medium. Speed and wavelength are given. We have to find out the wavelength of the light in air. We know that V is equal to nu lambda. Okay, so velocity in air, V in air will be lambda in air divided by velocity in medium will be equal to nu into lambda in medium. Frequency remains the same. So nu and nu cancels out. We have divided these two equations. Okay, velocity in air is given as 3 into 10 raised to power 8 meter per second. And the velocity in the medium as given in the question is 1.5 into 10 raised to the power 8 is equal to lambda in air has to be determined and lambda in medium is 230 nanometer. No need to convert it in meter because lambda in air will get it in nanometer. So on simplifying it, we get lambda in air to be 460 nanometer. So the correct option is C. Next is which one of the following materials does not exhibit emission of electrons when irradiated by the visible light? Okay, rest all emit. Cadmium does not emit. Next question, a hydrogen atom makes a transition from n is equal to 5 to n is equal to 1, then the wavelength is lambda. When it makes a transition from n is equal to 5 to n is equal to 2, we have to find out lambda. That is the wavelength. We know that 1 upon lambda is equal to Rydberg's constant or 1 upon n2 square minus 1 upon n1 square. So 1 upon lambda is r when it is making the transition from 5 to 1. So n2 here is equal to 1 minus 1 upon 25. So simplifying this, we get r is equal to 25 upon 24 lambda. Okay, now let's come here. When it makes the transition from n is equal to 5 to n is equal to 2. Let the wavelength is lambda dash. So we can write 1 upon lambda dash is equal to R. Again using the same equation, 1 upon N2 square minus 1 upon N1 square, 1 upon 4 minus 1 upon 25. So 1 upon lambda dash is equal to R into 21 upon 100. Okay, or you can write down lambda dash is equal to 100 upon 21 into lambda. Now what is lambda? 25 upon 24 lambda. Okay, so here we are substituting this R is equal to 25 upon 24 lambda. So on simplifying it, we get it to be 32 upon 7 into lambda. So the correct option is D. Next question. Question number 12. The curve of binding energy per nucleon as a function of atomic mass number has a sharp peak for helium nucleus. So helium nucleus is, we have to find out the correct option. The correct option is the helium nucleus is more stable as compared to its neighbors. Question number 13. In extrinsic semiconductor, the number density of the holes is given and the number density of the intrinsic charge carriers is given. So here we have to find out the number density of the electrons. We know that Ni square is equal to Ne into Nh. So Ne, which is the number density of electrons, will be equal to Ni square, number density of intrinsic charge carrier square upon Nh. Ni is given 1.2 into 10 raised to the power 15 minus 1.2 into 1.2 into 10 raised to the power 15 square will be 30 upon 4 into 10 raised to the power 20. Okay, on simplifying it, you get to be 3.6 into 10 raised to the power 10, into 10 raised to the power 9 per meter cube. So the correct option is C. Next is pieces of copper and of silicon are initially at room temperature, both are heated. We know that the conductivity of metals decreases and the conductivity of semiconductors increases with the rise in temperature. So the correct option is D. Next question, the formation of depletion region in a PN junction diode, it is due to diffusion of the electrons as well as the diffusion of holes. So B option is correct. Question number 16 is diamagnetic materials exhibit magnetism, which is true. Diamagnetic materials do not have permanent dipole moment. This is also true. But the reason is not the correct explanation of the assertion. So the answer will be B. Next is work done in moving a charge around the closed path in an electric field is 0. Absolutely correct. And the electrostatic force is conservative. Conservative forces are those due to which the work done in a closed path is 0. So the reason is the correct explanation of the assertion. Hence the option is A. Next is in Young's double slit experiment, all the fringes are of equal width, which is true. And the fringe width depends upon, we know that the fringe width in the interference pattern is given by lambda d upon small d. So it is depending upon all these three factors. So this is also true. And the reason is the correct explanation of assertion. Hence, the correct option is A. Next is question number 19. Now these are 2-mark questions. Explain briefly how and why a galvanometer is converted into an emitter. Okay, these are also short answer questions. Okay, first you have to answer why a galvanometer is converted into an emitter, as the galvanometer is a very sensitive device. So for measuring current, it has to be converted into emitter. And how the galvanometer is converted into an emitter? by connecting the shunt resistance, a very low resistance, a very small resistance in parallel to the galvanometer. Next is how are infrared rays produced? They are produced by hot bodies. All hot bodies, they produce infrared waves. Why are these waves referred as the heat waves? Because they are readily absorbed by the water molecules and they will increase their thermal energy and it will increase the temperature of its surroundings. That is, it will heat the surroundings. So that is why they are referred as the heat waves. Give any two uses of infrared waves. Any two uses you have to write, like it is used in greenhouse effect, it is used in remote switches, okay, and any other two reasons could be written. Next is how are X-rays produced? When the fast moving electrons, they hit some heavy target, then the X-rays are produced. And any two uses of this, they are used for studying the crystal structure. They are also used for the treatment of certain forms of cancer. They are also used as the diagnostic tool in the medicine. Okay, so any two uses have to be written. Next question, in the given figure, the radius of curvature of plano-convex and plano-concave lens is 15 centimeter. Okay, and the refractive index is 1.5. You have to find out the final position of the image. Okay, first let's consider this plano-convex lens. Let's find out its focal length by using the lens maker's formula. 1 by f1 or 1 by f is equal to mu minus 1 upon 1 upon r1 minus 1 upon r2. Okay, for a plano-convex lens, we are finding out the focal length. Mu given here is 1.5. 1 upon r1. r1 is the radius of curvature of the first surface, which is a plane surface. So r1 is infinity. Minus r2. The radius of curvature here is given as 15 centimeter. Okay, so 15 centimeter, we measure in the opposite direction of the incident light. So this will be minus 15. Hence, you get the focal length of the plano-convex lens. F1 is equal to, on solving it, you get it to be 30 centimeter. Same way, first let's find out the focal length of the plano-concave lens. Using the same formula, let the focal length is f2. 1 upon f2 is equal to 1.5 minus 1. Now here r1 is minus r, that is minus 15. And r2 here is, as it's a plane surface, so it will be infinity. And 1 by infinity is 0. So on simplifying it, we get f2 to be minus 30 centimeter. So here we got the focal length of the plano-convex lens and the focal length of the plano-concave lens. Now, let's find out the final position of the image. First, the image formed by this plano-convex lens. For this, object is at infinity. So u1 is, because the rays are parallel, u1 is infinity and the focal length is plus 30. Using the lens formula, 1 upon f1 is equal to 1 upon v1 minus 1 upon u1. Okay, so substituting, 1 upon 30 is equal to 1 upon v1 minus 1 upon infinity. So here we get v1 is equal to 30 centimeter. That is, the image formed by the convex lens is at 30 centimeter from the convex lens. So the object distance for the concave lens will be 10 centimeters. 30 minus 20. So the object distance u2 will be 10 centimeters. And as it is along the direction of the incident light, so u2 will be taken as plus 10 centimeter. Again, use the lens equation. 1 upon f2 is equal to 1 upon v2 minus 1 upon u2. f2 here is minus 30. v2 you have to determine. And u2 is 10 centimeter. Okay, so on simplifying it, we get v2 is equal to 15 centimeter. So the image is formed 15 centimeters towards the right of the concave lens. This is the position of the final image. Let's proceed to the next question, which is question number 22. Okay, question number 22 is what happens to the interference pattern when the two coherent sources are infinitely close to each other? We know that the fringe width is given by lambda d upon small d. Infinite close, so beta inversely proportional to d. When d is very, very small, infinite close, beta would be very large. That is, the fringe width will be very large. Now, in the second part, when they are very far apart from each other, beta will be very small, or you can also write that as the two coherent sources are very far from each other. So they will not interfere and no interference pattern could be seen. That is also correct. Next question. Question number 23, which is what is meant by ionization energy? Okay, it is the minimum energy required to remove an electron from an atom. Okay, or to move an electron from n is equal to 1 to n is equal to infinity. And what is its value for the hydrogen atom? It is 13.6 electron volt. Next question is mass defect. Mass defect is the difference in the mass of the nucleons and the mass of the rest nucleus. Mass of nucleons means mass of protons, whatever inside the nucleus, we call it as nucleons. We know that protons and neutrons are inside the nucleus. So mass of nucleons is mass of protons plus the mass of neutrons. So there is a difference between the rest mass of the nucleus and the mass of nucleons. So this difference we call it as the mass defect. Okay, how is it related to the stability of the nucleus? We know that binding energy is equal to delta m into c square. Delta m is the mass defect. And binding energy per nucleon, it determines the stability of the nucleus. Binding energy per nucleon, more stable. And how is it possible when the mass defect is more? So the answer is the binding energy per nucleon represents the stability. More the mass defect, more will be the binding energy per nucleon, and more stable will be the nucleus. Next is draw the energy band diagram for the N-type and the P-type semiconductor at T greater than 0 Kelvin. Okay, as you know, we have to draw valence band, conduction band above the valence band. In case of N-type of semiconductor, the donor energy level is formed just below the conduction band. How much below? 0.01 electron volt below. Okay, and in case of N-type of semiconductor, we know that the number of electrons are more, number density of the electrons are more. So here you will draw more number of electrons and few holes. Number density of electrons is greater than the number density of holes. Whereas in P-type, again, you will draw valence band, conduction band. And here, the acceptor energy level is just above the valence band, which is 0.05 to 0.01 electron volt. But here, the number density of the holes will be greater than the number density of the electrons. So you will draw more number of holes as compared to electrons, and few electrons can jump over here also due to the thermal education. So this is for P-type, this is for N-type. Next is answer the following questions. A PN junction diode is damaged by a strong current. Yes, it is damaged because strong current, it will get heated up and a large number of covalent bonds will be broken. So that is why it will get damaged. Impurities are added in intrinsic semiconductors to increase its conductivity. Next is section C. In section C, the questions are 3 marks each. Question number 26, A part. Two charged conducting spheres of radii A and B are connected to each other by a wire. Find the ratio of the electric fields. We know that whenever two spheres or two charges or two capacitors, anything, when they are connected by a conducting wire, charges flow from high potential to low potential till the charges become the same, till the potential become the same. The charges are shared so that the potential becomes the same. Okay, the potential for the A sphere, for the first sphere, we know is equal to KQ by A. So KQ1 upon A. The potential becomes the same. So KQ2 upon B. So from here we can get Q1 upon Q2, which is equal to A upon B. Okay, now electric field is KQ1 Q2 upon R square. So the electric field of the first sphere to the electric field of the second sphere will be equal to KQ1 upon A square upon KQ2 upon B square. So this comes out to be Q1 upon Q2 B square upon A square. From here Q1 upon Q2 is B by A. Q1 upon Q2 is A by B. So A upon B into B square upon A square. What do we get the ratio? B is to A. Hence the ratio of the electric field is B is to A. Okay, there's a choice. B part is a parallel plate capacitor. C is charged by a battery. It is disconnected and connected to another uncharged capacitor whose capacitance is C. Find the ratio of the final charges. Okay, so we know that Q is equal to C into V. Q is equal to C into V. So Q for the A capacitor will be equal to CA into V1 and Q for B capacitor will be equal to CB into V2. Now here CB is given as 2C, CA is given as C. Okay, and when they are connected, again they'll come to the same potential. So V1 will be equal to V2. So QA upon QB will be equal to CA upon CB. CA is C and CB is 2C. So the ratio is 1:2. Okay, B part, the total electrostatic energy in A and B and that stored in A initially. Okay, electrostatic stored energy in initially. Let's find out first. Initially in capacitor A will be equal to half C1, C1 is C into V square, half C1, V1 square and V1 is equal to V. So this is the initial energy stored in the capacitor A. Okay, now let's find out the final energy stored in both the capacitors. For that, first we have to find out the common potential. Whenever two capacitors charged to different potentials are connected, they come to the same potential and that potential we call it as the common potential, which is given by C1 V1 plus C2 V2 upon C1 plus C2. Here V2 is 0 because it is uncharged. V1 is V, C1 is C and C2 is 2C. So what do we get? C into V, V2 is 0. This is 2C plus 1C, 3C. That is, this is equal to V by 3. This is the common potential. Okay, now let's find out the final energy stored in the capacitor. I'm writing it over here. Will be the energy stored in the capacitor A final and the final energy stored in the capacitor B. Formula for the energy is half C1 V1 square. So half C1 here is C and which potential do they reach? Both of them reach to the common potential and the common potential is V by 3. Okay, half C into V square. V here is equal to V by 3. The same way, half CV square. What is C for the B capacitor? 2C into V by 3 whole square. Okay, on simplifying it, we get half C into V square upon 9. We can take it common. 1 plus 2. That is, this is equal to 3. So we get half CV square 3 upon 9, half CV square upon 3. Now what do you have to find out? Electrostatic, the ratio of the electrostatic energy finally upon initial. UF upon UI. This is UF This is ui. So when you solve it, what do you get? You get the ratio to be 1:3. So the answer is 1:3. Question number 27. Define current density, current flowing per unit area, relaxation time, the average time between two successive collisions. Okay, derive an expression of the resistivity of a conductor in terms of number density and the charge carriers. This is a simple derivation. Okay, we find out starting from I is equal to NEA VD, where N is the number density of the electrons, VD is the relaxation time, and VD here is equal to E upon M into tau. Okay, then V upon E can be put as V by N. Find out V by I, will get the resistance and compare it by R is equal to rho L upon A. So we get the resistivity. That resistivity comes out to be M upon N E square into tau. This is the simple derivation. Okay, so this will be the resistivity in terms of relaxation time and the number density of the charge carriers. Question number 28, which is from alternating current. Okay, it was a very simple question, very difficult. Okay, it's a CR circuit. And in case of a CR circuit, all these values are given. And first part, A part, we have to find out. I'm writing over here. A part, the impedance of the circuit. Impedance of the circuit, Z is equal to under root R square plus XC square. R is given as 200 ohms. Now let's find out XC. XC is equal to 1 upon 2 pi mu into C. All these values are given. 1 upon 2 pi mu is 50 hertz and the capacitance is 50 upon pi microfarad. So micro is 10 raised to the power minus 6 farad. Simplifying it, this also you get it to be 200 ohms. So R is 200, XC is 200. Hence, Z, the impedance is equal to under root 200 square plus under root 200 square. Under root 200 square plus 200 square, which is equal to 200 into root 2 ohms. So this is the value of the impedance, 200 root 2 ohms. Now the B part is phase angle. Phase angle, we know that tan pi is equal to XC upon R. XC is 200, R is 200. So tan pi is equal to 1. So pi is equal to 45 degrees. So the phase angle is 45 degrees. Next is the voltage across the resistor. Voltage across the resistor, VR is equal to IRMS into R. Okay, IRMS can be written as VRMS upon Z into R. Okay, now how to find out VRMS? This is V naught or V naught, 100 volt. So VRMS will be equal to V naught upon root 2. V naught is 100 upon root 2. This is VRMS into R. R here is 200 ohms and Z here is equal to 200 into root 2. So on simplifying it, we get to be 50 volts. Hence, the voltage across the resistor is 50 volts. Next question, question number 29. Define critical angle for a given pair of media. We know that critical angle is whenever the ray of light is passing from denser to rarer medium at a particular angle of incidence, the refracted ray grazes over the surface separating the two media. That is, the angle of refraction in the rarer medium is 90 degrees. This angle, we call it as the critical angle of incidence. So it is that angle of incidence whenever the ray of light is passing from denser to rarer medium, the angle of refraction in the rarer medium is 90 degrees. Now obtain the relation between critical angle and the refractive index of the medium. Okay, so when it is passing, this is the denser medium, this is the rarer medium. So the refractive index of second medium with respect to first, that is rarer medium with respect to denser medium, will be equal to sine IC upon sine R. Angle of refraction in the rarer medium is 90 degrees. So you can write down sine 90. Okay, and the refractive index of the denser medium with respect to rarer will be 1 upon the refractive index of the rarer with respect to denser. So this can be written as sine 90 upon sine IC. So the refractive index of the denser with respect to rarer is 1 upon sine IC. So this is the relation between the refractive index and the critical angle of incidence. Next question, distinguish between nuclear fission and fusion with one example of each. I think all must have done, very simple. The release of energy in nuclear fission and fusion on the basis of the binding energy per nucleon. Okay, we know that the binding energy per nucleon of the products in any of the nuclear reaction will be greater than that of reactants. There's a choice here. How is the size of the nucleus found experimentally? By the method of scattering, it is found out experimentally. Relation between the radius and the mass number of the nucleus. We know that the radius of the nucleus is equal to empirical constant, some constant, we call it as the empirical constant, a raised to the power 1 by 3. So this is the relation. Prove that the density of the nucleus is independent of the mass number. We know that density is mass upon volume. Okay, mass of the nucleus is the mass of nucleons. Let one nucleon is having a mass number small m, and how many nucleons are there? Mass number. So what is the mass of the nucleus? Small m, mass of one nucleon into the total number of nucleons, which is the mass number. And the volume, as it's a sphere, the nucleus is a sphere, 4 by 3 pi r cube. Substituting this r is equal to r naught a raised to the power 1 by 3, we get 4 upon 3 pi r naught cube a raised to the power 1 by 3 into 3. We get it as a and a cancels out. So this is the expression for the nuclear density, which is independent of the mass number. Next is section D. Section D is consisting of 3 questions, 5 marks each, and each question has a choice. Question number 31. Gauss law to find out the electric field due to a long line charge. This is a very simple derivation. E is equal to lambda upon 2 pi epsilon naught into r. So you have to derive this equation. Next is this long line charge. Suppose positive charge is uniformly distributed. Now it's given that an electron is moving in a circular path with the line charge at the center, with this line charge at the center. Okay, now find the kinetic energy. As this electron is revolving, so which energy will it possess? It will have kinetic energy. Okay, so that expression of kinetic energy you have to determine. Okay, as it is revolving in a circle, the necessary force, centripetal force, which we know is equal to mv square upon r, should be equal to the electrostatic force on the electron, which is equal to q into e. Q is what? The charge on the electron, which is small e. And the electric field is how much? Lambda upon 2 pi epsilon naught into r. So mv square upon r, q here is e, and the electric field is 2 pi epsilon naught into r. R and r cancels out. We have to find out the expression of kinetic energy. So multiply left hand side, right hand side, both by half. So we'll get the expression for the kinetic energy, half mv square is equal to E lambda. Here also we have to multiply by half. So 4 pi into epsilon naught. This is the expression for the kinetic energy. C part is draw the graph between kinetic energy and the linear charge density. From this expression, we see that kinetic energy is directly proportional to lambda. Hence, the graph will be a straight. There is a choice in this question. Two identical point charges, let both are Q, situated at 0, 0 and A0. Is there a point on the line joining at which the electric field is 0? If we find the electric field at the midpoint due to this Q charge, it will be pointing away from this charge, and due to this Q charge, again it will be pointing away. That is E1 and E2, both are equal in magnitude but opposite in direction. So at the midpoint, the electric field is 0. Why? Because as the electric field is a vector quantity, due to these two charges, the electric fields will be equal in magnitude and opposite in direction. Electric potential. Potential is a scalar quantity. So the potential at midpoint will not be equal to 0 at any point in between. So the potential will not be equal to 0 at any point. Second part is state the significance of negative value of electrostatic potential energy. Negative value of electrostatic potential energy means the charges are bound together. Or you can say that the forces which are acting will be attractive in nature. Now there's one numerical. Three charges at the vertices of an triangle, which is equilateral triangle. So the potential energy we know is equal to K Q1 Q2 upon R. K Q1 into Q2, between these two charges, the potential energy will be 4 into minus 4 minus 16 upon R. R here is 2 meter. Okay, now these are in microcoulombs. 4 into minus 4 into 10 raised to the power minus 6 into 10 raised to the power minus 6. That will multiply outside the bracket. Okay, plus between these two charges, minus 4 into 2, minus 8 upon the distance between them is 2. Between these two charges, 4 into 2, 8 upon 2. Okay, all these are in microcoulombs. So into 10 raised to the power minus 6 minus 6. So this will be 10 raised to the power minus 12. Minus 8 by 2 plus 8 by 2. You can cancel out. K here is 9 into 10 raised to the power 9. Minus 16 by 2 is minus 8 into 10 raised to the power minus 12. So this is equal to minus 7.2 into 10 raised to the power minus 2 joules is the answer. Define coefficient of self-induction. L is equal to coefficient of self-induction. We represent it by capital L. L is equal to phi upon I, magnetic flux per unit current, or L is equal to induced EMF produced upon rate of change of current upon di by dt. Okay, obtain the expression of the self-inductance in terms of length, cross-sectional area, and number of turns for a long solenoid. This is a simple derivation which comes out to be mu naught n square A upon N. Next is calculate the self-inductance by this AC source whose frequency is given, and this is for the DC source. Okay, so from the AC source, we can find out Z. Z is equal to V upon I. So V here is 6 upon 1, or you can say 3 upon 0.5. So Z comes out to be 6 ohms. From the DC source, you can find out the resistance. R is equal to V upon I, 4 upon 1, 4 ohms. Okay, so here we got the Z. Now impedance you can find out. Z is equal to under root R square plus XL square, or Z square is equal to R square plus XL square. So from here we can find out XL square, which is equal to Z square minus R square. That is 36 minus 16, which is equal to 20. So XL is equal to under root 20 ohms. Okay, now as you have to find out the self-inductance, XL we know is equal to 2 pi nu into L is XL. XL we have determined under root 20. 2 into pi into nu here is 200 upon pi, and L has to be determined, and XL is under root 20. So pi and pi cancels out. L is equal to under root 20 upon 400 Henry. So this will be the value of L. This can be calculated. I think it comes out to be 11 millihenry. There's a choice. Describe the principle and working of AC generator. Principle is EMI, electromagnetic induction, and the working you have to explain, okay, with the diagram, and explain, obtain the expression of instantaneous value of the EMF generated. The peak value of the EMF generated is equal to E naught is equal to NBA omega, and the instantaneous value is equal to E naught sine omega t. So this you have to derive. Very simple. Okay, so in this choice question, the second part is the coil of generator, all these values are given. You have to find out the maximum EMF. Maximum EMF we derive is equal to NBA omega. All these values are given. Only you have to substitute. N here is number of turns, 100. Magnetic field is 0.8. Cross-sectional area is 0.5. And omega is 60 radian per second. So this comes out to be 2400 volt. And the power generated, power dissipated will be equal to, sorry, it's not the power generated, power dissipated. Power dissipated is equal to ERMS square upon R. Okay, it will not be the E naught. ERMS square upon R. E naught we have found out. ERMS is equal to E naught upon root 2. That is 2400 upon root 2 square. This is ERMS square upon R. Resistance here given over here is 100 ohms. So on calculating it, we get to be 28.8 kilowatt. Question number 33, state Huygens principle. With the help of diagram, you have to verify the laws of reflection. You must have done this. Okay, very simple. Then the B part is, we have to find out the distance of the object from the mirror. It's a concave mirror. So using the mirror formula, 1 upon F is equal to 1 upon V plus 1 upon U. Okay, but here focal length is given, but V and U are not given. Instead, it is given that virtual image is formed, which is 3 times magnified. And we know that magnification in case of a mirror is minus V by U. And this magnification will be equal to plus 3. Why? Because it's a virtual image. So V is equal to minus 3U. V is equal to minus 3U. So simplifying it, what do we get? V is equal to, substitute it over here, 1 upon F, 1 upon 12, as it's a concave mirror, so the focal length will be negative. V here is minus 3U plus 1 by U. So on simplifying, you get U is equal to minus 8 centimeter. Okay, next is, again there's a choice over here. Draw a label diagram showing the formation of the image by a refracting telescope. Define the magnifying power and the 2 limitations of refracting telescope over a reflecting telescope. Okay, a reflecting telescope is better than a refracting telescope because in case of a refracting telescope, chromatic aberration, spherical aberration may arise because we have to take the aperture to be large for an objective lens. And so these aberrations may arise, spherical aberration, chromatic aberration, which does not arise in case of a reflecting telescope. Also, in case of a refracting telescope, the image is not as bright as that in case of a reflecting telescope. Then there's the numerical over here. The focal lengths of objective and eyepiece are given. If the tube length of the microscope is, you have to find out the tube length if the magnification is 300. So using the formula, magnifying power is equal to L upon FO D upon FE when the final image is formed at infinity. So magnifying power given as 300, length of the tube has to be determined. Focal length of the objective is 1 centimeter. D 25 centimeter and Fe is 2.5. So we get the length to be 30 centimeter. So the length of the microscope tube is 30 centimeter. So this is question number 34. The figure is made. Explain the reason of jumping of the ring when the switch is closed. Okay, so this ring jumps because the induced current is produced in it. What will happen if the terminals of the battery are reversed? The direction of the current will be reversed. Okay, but still the ring will jump because the induced current will be produced. Explain the two laws that help us to understand this phenomenon. The two laws are Faraday's laws of EMI. That is, whenever there is a change in magnetic flux linked with the coil, an induced current is produced. And the second is Lenz's law, which states that the induced EMF produced will oppose the rate of change of magnetic flux. Okay, then there's a choice over here. Briefly explain the various ways to increase the strength of the magnetic field inside a solenoid. We know that inside a solenoid, the magnetic field is given by B is equal to mu naught Ni upon L, number of turns upon length into I. So by increasing the number of turns, by increasing the strength of the current, or by decreasing the length, or by placing some iron core inside it so that its permeability increases, then mu naught will be, then mu will be equal to mu naught into mu R. Okay, so by introducing a soft iron core, then also the magnetic field inside increases. Okay, then question number 35, the last question, which is again a case-based study question. Light beam has the highest frequency and why? The one which is having the maximum value of the stopping potential, that is B, is having the highest frequency because its stopping potential is maximum. Longest wavelength, the one which is having the lowest stopping potential. C is having the longest wavelength because its frequency is minimum, or you can say the stopping potential is minimum. Stopping potential is the retarding potential to reduce the photoelectric current to zero. Okay, maximum momentum, we know that momentum is equal to under root 2m into kinetic energy. The one which is having the highest kinetic energy will have more momentum. And kinetic energy, we know, is equal to, according to the Einstein's photoelectric equation, EV naught is equal to, which is kinetic energy, is equal to h nu minus h nu naught. So the one which is having the highest frequency will have the highest kinetic energy. Highest frequency, the one which is having the highest stopping potential. So B here is having the highest stopping potential. So highest frequency, highest kinetic energy. So its momentum will be highest. There's a choice. What is the effect on threshold frequency and stopping potential on increasing the frequency of the incident beam of light? Okay, threshold frequency does not depend upon the frequency of the incident beam light. Threshold frequency depends upon the metal. So it is not affected on increasing the frequency of the incident beam light. Whereas the stopping potential is affected. Okay, again by using Einstein's photoelectric equation, E into V naught is equal to h nu minus h nu naught. Okay, on increasing the frequency, the stopping potential increases. Hope you understood all the questions. Thanks for watching. Thank you.